Hey guys, so we want to pick up where we left off yesterday, Tuesday, excuse me. So Tuesday we were reviewing section 2.4 and we were discussing uninhibited growth and limited growth. So let's see if I can share what I have here, the PowerPoint. So last class we discussed PowerPoint problems, functions. We discussed uninhibited growth that was in this form. The functions could be modeled by y equals ce with the power of kx. So remember that is uninhibited growth. But everything cannot be modeled. Population growth, not all growths will be modeled by uninhibited growth. There's times where there's elements present that can limit population growth. For example, if there's a depletion of resources, population growth can slow down or stop at a certain point. So that's what we're going to discuss today. So I have here a new equation for you guys. So I want you to write this down, and I want you to understand that this models growth when there is a limit to that growth. If there's resources and they've been depleted, this can model the maximum growth. There's going to be a point at which growth stops. We're going to limit that growth. And remember, you can pause this video if you need to write this down. But I'm going to move on to the next slide because I want to show you what this looks like when you graph it. So here's an equation. Here's a model of limited growth, or what we may call this. On the last slide, they refer to this as a logistic equation. When we graph a logistic equation, you can see how there's growth there, and it kind of shoots up really quickly at some point, but then it levels off. There's like an asymptote. There is an imaginary line where that equation is approaching, but it will not cross, because that is where our population is. That's the value at which it is limited. So we're going to use that to answer or solve this one last problem that we didn't get to in class. And in this case, we're going to discuss an infection and how it grows at a university. So example 4, it says spread by skin-to-skin contact or via shared towels or clothing. I just refer to this as MRSA. You science people probably know the correct word here. But it can easily spread. It's an easily spread staph infection. In other words, it's going to spread easily through the university. I lost my spot here. But it says left unchecked, the number of cases of MRSA on a university campus T weeks after the first case can be modeled by this function. So they give us n of t, and they've modeled for us. That's the model that that models the growth of MRSA on campus if there is nothing there to combat what's happening. So using that information, we want to answer these 3 questions. Part A, it says find the number of infected students after 3 weeks, 40 weeks, and 80 weeks. And then part B, we want to find the rate at which the disease is spreading after 20 weeks. And then we want to explain why an uninhibited growth is inappropriate, but a logistic equation is appropriate for this situation. And of course, you guys can use a calculator to graph this so that you can look at it and kind of see what's going on. So let's jump into this. I'm going to dim my lights. So hopefully, if all works well, you won't see me so much, but you will see my problem. You will see the problem with these neon markers light up here. So fingers crossed that this works the way we want it to, okay? All right, so you have your problem, and what we want to do for part A, oops, I turned my black light off. Part A, I want to find I'm not going to do all three of these because honestly, if you can do one of these for part A, you can do three of them. It's only a matter of substitution, taking those numbers and substituting those into the problem. So what we're going to do is we're going to find n of 3. That is for 3 weeks. We want to know the number of infected after 3 weeks. So literally, all that's going to take is you guys taking that 3, and I do not have my equation here. Let me find it. N of 3 is going to be equal to that 568.803 divided by 1 plus 62.200, and there we're going to have our E, and we're going to raise that with an exponent of negative 0.092. And because we want to know the number of infected, I should probably put this there. Number of infected at 3 weeks. Let's see. So let's turn this just a bit. So what I would do is in that equation, I would substitute 3 into there. And I'm not going to make this too difficult. You guys can plug this into your calculator and you can try this on your own. But N of 3, let's see, let's find my answer. If I do that, that's going to be 11.8. So what does that tell me? That says, so approximately 12 students are infected after 3 weeks. So I want to make sure that we can understand exactly what this means. So whatever number, you can try these again, and I would for the other pieces to part A, they did ask for 40. So if we find N of 40, you can try this on your own. N of 40 is equal to 221.6, and then that last one, N of 80, you can try this on your own, is 547.2. So again, you can try that on your own time. That is no more than a calculator problem for you to substitute. All right, so let's take this a bit further. Now, part B asks us to find the rate at which this disease is spreading on campus at a particular time. So, what we want to do is at 20 weeks, we want to find the rate at which Mercer is spreading on campus. But before I can find my rate, what I need to find is the derivative of that equation that was given to me. Well, let's see if I erase, let's take this little notch off here. This can be hard to erase. So the original function was, just so I can have it for reference to look at, that was 563.803 divided by 1 plus 62.200 times E with the exponent of negative 0.092 t. So now if I want to find the derivative of this thing, guys, what we want to do is use our quotient rule. So the derivative is going to be the bottom times the derivative of the top. And in the top we have a constant. That's going to be 0. The bottom times the derivative of the top minus, let's see if I can move my camera over just a bit, minus the top times the derivative of that bottom. The derivative of the bottom is going to be found by taking the derivative of 1, which is 0, then the derivative, remember you have two pieces here we want to take the derivative of in the bottom. The derivative of 1 will be 0, but the derivative of that 62.200, all of that, remember, is going to be just what that is because it has an e in it. Remember how we found the derivative of e's? You leave it exactly the same times, and I'm running out of room right there. Remember, we always multiply by what is in that exponent, which is 0.092. I'm running out of room. So that would be e to the u times du is what I did there essentially. My board is short, so I don't really have room. Now, that's the bottom times the derivative of the top minus the top times the derivative of the bottom all over that bottom squared. So that's what we would have. Now, if I want to clean this up a bit, let me bring this over so I have some room. If I clean this up a bit, what will that look like? Well, this is gone because that's 0 there. And what I'm left with in the bottom, let's get a different color. I have a minus here, right? But I also have a minus there. And a negative times a negative is going to be a positive. And then what I want to do is multiply those numbers. I have this 563.803, and I need to multiply that because remember that's on the end. I just didn't have much room. Times that 0.092, and if I multiply those numbers together, that would give me 52.32329876. So we're not going to round off just yet. We want this to be as precise as possible. Then we're going to bring that e down, which would be that 62.200 e to the negative 0.092 t divided by 1 plus 62.200 e. All of that stays exactly the same in your denominator. Now, what we want to do, that's pretty much it. We can leave it just in that form. We don't. There's no point in multiplying this out. If you know, we could multiply these two numbers out, but we don't have to, because our last step, what we want to do is we want to find the rate at which it is spreading through campus at 20 weeks. So then what we would do is take 20, and we would substitute that 20 into this function. And if I did that, let's see, do I have room to write this? That would look like, that would be exactly 52.329876 times 62.200 e with all of that exponent. Can't leave anything off. We're going to put times 20 up there. And then in your denominator, we're going to leave it exactly the same. Yes, we can still see everything. And again, in the place of that t, we're going to put 20 there. And I suggest that you guys try this, because a big problem is not understanding that we need to substitute, but actually substituting and actually getting the correct answer. And if you do that, guys, what you would get is approximately 4.368. And what this tells me is that after 20 weeks, the disease is spreading through the campus at a rate of approximately 4 cases per week. All right, so, and I'm not going to write this last part down. I'm just going to say it, and you can write it on your paper. Remember, you can pause. But it's saying explain why an uninhibited growth model is appropriate, but this logistic model is. So remember that unrestricted growth is inappropriate for modeling this situation, because as more students become infected, there's going to be fewer people or fewer students on campus that can become infected. So the logistic equation displays the rapid spread of the disease initially. It shoots up really quickly, as well as the slower growth at the end. So as there's less people to be infected, it's still going to grow, but it's the rate of infection is going to slow down. So that is why this logistic equation would be most appropriate for modeling this MRSA outbreak at a university. Again, to say that one more time, when the outbreak begins, there's a lot of uninfected people on campus. So that infection rate will rise really quickly, right? But at some point, there's going to be as more people become infected, less people are going to be, the disease, they won't be available. If they're already infected, there's less number of people for the disease to infect on campus. So as that happens, the rate at which this disease spreads on campus decreases. So therefore, this logistic equation, or this logistic function, is the best for modeling this situation. All right, I hope this helped. If you guys have any questions, don't hesitate to reach out. All right.